Hi, my name is Anshikatiman, and this is my presentation on the multiverse, an exploration into the potential existence of multiple parallel realities. So, the concept. The multiverse theory is the belief of the existence of a larger extension of our visible universe, one of which our universe is only a tiny fraction of. In the variety of hypotheses, there are claims to the presence of more universes, albeit disconnected to each other, but potentially possessing similar features to ours, providing ground for the existence of a parallel reality. The broad nature of the theory calls upon a multitude of different parts of theoretical physics, but also engages in the debate of philosophy, making the topic more interesting, but also more confusing to interact with. So, in regards to the explanation of the multiverse, the most prominent explanation comes from a cross application of quantum physics and cosmology, in which the first prong is in regards to cosmic inflation. Cosmic inflation is the theory of a massive and rapid universal expansion that took place right before and right after the Big Bang. For some contextualization, when it comes to the theory of cosmic inflation, it was set up in order to answer the gap in research that existed within the Big Bang theory. More specifically, under the Big Bang theory, there is a belief that the cosmological horizon, a point that denoted the farthest point to which someone could see in their universe, was constantly moving. However, under this theory, there lied an issue in which the regions that had not been exposed to that cosmological horizon ever before for some reason already had the same conditions as the regions that had been exposed, bringing into question what led them to already have those conditions. This is where the inflation theory became key. It predicted that the cosmological horizon was actually stationary and that the regions moved through and around it, acting to expose all regions to these same conditions, providing the explanation for the pre-existing similarity. This principle was what acted to explain the conditions of an expansion, but also the nature of how events like the Big Bang actually took place. Furthermore, providing evidence of a universe where the expansion is not just limited to us, but to that of the multiple different regions as well. This also acted to provide evidence for the massive nature of our universe, with emphasis on the existence of it beyond our visibility. So the second prong of this came from the quantum field theory, a very prominent part of quantum physics as a whole. For a very simple explanation of this is that, for the purposes of this concept, is that the quantum field theory is the practice of dealing with particles over large infinite quantum fields. So the inflation is viewed, so in regards to the cosmic inflation, this inflation is viewed upon the basis of the quantum field theory, in which it is believed to have field values that vary randomly, which indicate the time to which cosmic inflation takes place. The higher the field value, the longer that the cosmic inflation takes place, and the lower the field value, the shorter that the cosmic inflation takes place. Dr. Ethan Siegel, a prominent astrophysicist, explains this concept best while comparing it to a ball on a hill with a flat surface on the top. As the ball rolls on top of the hill, it experiences the cosmic inflation, but once it reaches the sloped part of the hill, it begins to roll down, and that is where the energy conversions start to take place, in which all the energy from the quantum field start being converted into the matter and energy that eventually will lead to an event like the Big Bang to occur after all the energy has been converted. In terms of a very short cosmic inflation, similar to that of our universe, the potential for a Big Bang-like event increases, possibly allowing for a universe in some way similar to ours to have been created. So for a little bit more contextualization on a very short cosmic inflation, our cosmic inflation in which the Big Bang took place took place for only 10 to the negative 33 seconds before and after. So it was a very, very short period of time. Insofar as that was true, and as we've stated before, that the field values vary randomly in every single scenario, if there were to be a time and place where the field value were to randomly vary to a value that was very similar to ours, this could potentially increase the chances of a Big Bang-like event taking place, and also increase the chances of conditions to that similar to that of our universes to take place, allowing for a similar universe to be created, which also feeds into several different parts of the multiverse theory that we will get into a little bit later. The key nuance in regards to the quantum field theory is that these cosmic inflations are consistently occurring within our universe, within our visible universe, evidenced by things like the CMBR, which is the cosmic microwave background radiation, which is occurring all around us at all times, as well as the outside of our visible universe with the varied values allowing for the creation of different universes, as stated before. So a more recent and hypothesis in regards to the explanation of the multiverse is the Hawking-Hertag model. This model was published shortly before the death of Stephen Hawking, and it discusses the claim of multiple inflationary periods that created multiple universes, the same principle of the inflation theory that we just discussed. However, he finds issue with the normal theory due to the lack of certainty in the uniformity of the principles of science and mathematics that allows them to come to such conclusions. The reasoning for this is that there is no guarantee that the principles of math and science used in our universe are applicable to the other ones we are hypothetically studying. So, in order to reduce that issue in some way, they use holography, which is a use of technology in order to convert 3D models into simpler 2D representations, which both scientists predicted the universe to be finite upon a 2D model, allowing for increased testability and a reduction in the broad possibility. They simplified a complicated and fragmented model into a simple and easy to understand build, and they also reduced the amount of possible universes to a significant amount, to still a very significant amount, but a smaller amount that were more quality in terms of the research that was able to be taken on them, and increasing the testing quality of those universes to allow for better overall results. This model and this overall research paper was titled A Smooth Exit from Eternal Inflation. So, the Hawking-Hertag prediction shines light on another key issue in the study and research of this concept, as there is no guarantee of the principles of our mathematics and science being the same in those of the other universes. This is one of the many factors that makes the study so difficult to engage with, but theoretical physicists still gain new findings through holding notions like the similarity of scientific concepts for simply the means of academia and getting a better understanding of what we can in regards to cosmic forces with what we have accessible to us right now. So, for example, that is what is denoted by the 1 plus 1 equals 3, 2 plus 2 equals 5. Sure, we hold these values of 1 plus 1 to equal 2 and 2 plus 2 to equal 4 in our universe, but in these alternate universes, in these different realities, and in these different universes, there's no guarantee of these mathematical principles to be true, and that is what allows for the difficulty in assessing these very complicated situations. Some recent developments in regards to this theory took place. A recent finding took place in 2017 that could potentially be evidence for another universe, in which researchers in the United Kingdom at the Durham University Research Center redesignated a cold spot, which is a spot where there's a significantly low temperature, on a constellation, specifically the Eridanus constellation, from a former supervoid to a possible dent from a multiversal collision. A supervoid is an area that lacks in the number of galaxies, having fewer than the normal amount within a constellation. The reasoning to which they identified it to be a possible dent from a multiversal collision was that it filled in the prerequisites to which they thought a multiversal collision would consist of. Things like the imprinting on the CBR, the cosmic background radiation, also causing major fluctuations in the level of radiation intensity, as well as taking on a round shape, which of course, as evidenced by this, that it did take on. So having recent developments like this, which took place very, very recently in 2017, provides a more tangible evidence for things that could be taking place in regards to multiversal developments, then that can allow us to better understand these things with more real and concrete evidence that we can use to study and better analyze and better evaluate. So shifting away from explanations of this and evidence of this and sort of the reasoning behind it towards the implications to which if a multiverse actually existed, what it would look like and the different aspects of it. This takes place within parallel and alternate realities. So Brian Greene, a very prominent theoretical astrophysicist who has written many, many different books about astrophysics and the existence of the multiverse, made the claim that there are only so many ways that matter can arrange itself within that of an infinite universe. Eventually, matter has to repeat itself and arrange itself in similar ways. So if the universe is infinitely large, it is also home to infinite parallel universes, and this, of course, lacks ground in the fact of the existence of the universe being infinitely large, that we, of course, discussed before. There is no sort of actual evidence or reasoning or backing behind this claim. However, it does act to hold merit within the fact that there is finite ways that events like, for example, the cosmic inflation could take place, and it also can potentially lead to events that have the ability to create universes similar to ours. So, as explained before, in regards to cosmic inflation and the quantum field theory, the quantum fields and the random amount of variation that they have of these quantum field values, if there were to be a situation where just based off of chance the value is assigned to that of very, very similar to that of our universe as we have right now, this has the increased potential to create a Big Bang like event, and that has the increased potential to create conditions that are similar to universes of ours. So even though there's not any sort of identical pattern, that like there's no guarantee that there's going to be an identical universe, Under these beliefs and under these findings that have been found, there is a slight possibility that there can be, under cosmic inflation and quantum field theory, that universes can be created that are similar to ours. So a little bit more on alternate realities. There's a little bit there's this is also where a number of different theories come into play in regards to the creation and existence of universes that express alternate realities. Most prominently shown under Hugh Everett, a graduate student at Princeton, who in his dissertation, his research paper, he contradicted the priorly established the Copenhagen interpretation. The Copenhagen interpretation claimed that the wave functions collapsed upon interactions with the classical world. What this basically means is that these wave functions under quantum physics would collapse, basically have a dramatic change in the state of matter of them within the interaction with the real world. This was disproven by several other things. For example, a very prominent example of something something disproving this was the Schrodinger's cat example. But Hugh Everett, most prominently in regards to his alternate realities theory, claimed that this was not true, and these wave functions actually would not collapse. This set path for the theory in which every outcome of any quantum measurement is experienced in another universe, an infinite amount of universes actually, opening up the theory of alternate realities. As shown by the example of this picture right here, to very simply explain it, it shows a prominent example of how even one decision that takes place within a single universe, the act of one choice versus another choice allows for the creation and the branching off to several other universes. That takes place in this example, where in which one response leads to another universe being created, another response leads to another universe being created, and the differences in the decisions that need to be made and the options that are provided allow for the different alterations and the differences and the changes that eventually allow for a branching of these alternate realities to take place. This alternate reality theory is by any means not proven, because of the fact, as we stated before, first of all, there's not an infinite number of universes that has currently been proven. We only understand that there may be an extension of our universe beyond of what we can see visibly, but we do not know if there's an infinite amount of universes. And the second issue comes within the fact that in regards to alternate realities, we do not know if these other realities that do take place have similar conditions to ours, because this alternate realities this alternate realities principle takes on the condition that these other universes have the exact same similar principles and the exact same conditions to that of our universe, and simply the decision-making process is the only thing that changes. So as of right now, this parallel and alternate realities theories are not to be proved whatsoever. They're simply theories, but as stated before, the ground in the fact that there may be some potential for similarities still does exist and still can allow for more example and more evidence in regards to theories along these lines. So to conclude, and a little bit on the scientific community's thoughts on this overall multiversal study, is that the scientific approval and reaction to the concept of the multiverse is very, very mixed. Some go as far as to say that it is a bad idea to discuss it altogether, as it erodes the values that science holds, like testability, as shown by things like the scientific method, in which you would like for a hypothesis to be able to be tested in order for it to be really, really considered a proper experimental hypothesis, while others embrace it as another challenge in understanding the wider scope of the cosmic forces which act upon us. This example of this second viewpoint is done by Brian Greene, as well as Ethan Siegel, which act to interact with this theory in more of a concrete and more substantive way, instead of just dismissing it as a whole. The biggest issue seems to be the lack of testability, as stated before, as well as the lack of observational security in terms of the issue, because of course we cannot see, because a lot of the belief in terms of this is seeing is believing, and not being able to observe these issues and observe these variables and these factors moves scientists to push this concept away as merely a metaphysical experiment or some sort of philosophical thought experiment, and not a real scientific concept that we can interact with. Also, the application of this concept into media and pop culture has acted to increase the interest, but also in some ways trivialize it into something that cannot possibly exist, and only something of mere of mere fiction, as shown by several different shows that, or several different ideals and things in pop culture that discuss it in a very trivial way. However, with all that being true and all that being said, it still remains an interesting theory to engage with and engage in, as a result, in either way, be it true or false, would be extremely world changing.